Hello, everybody, wherever you're in the world. We're going to go through the 2021 mechanics paper now. I've done the stats paper. This is mechanics. Again, should be too long, this one. So, shall we crack straight on with question number 1? Particle P moves with constant acceleration 2i minus 3j meters per second squared. At time t equals 0, P is moving with velocity 4i meters per second. Find the velocity of P at the time t equals 2 seconds for 2 marks. Alright, so what do we know? We know V has got to be 4i. It's a vector, so we'll underline it. We know the acceleration, which is given by 2i minus 3j. And what else do we know? Well, we know that time for t, which is what it wants, is 2 seconds. So we've got V, A, and T. We want to find... we've got U, that's U rather, that should, yeah, that's because the initial. V is what we want, so we can use V is U plus AT to get that. So we put in what we know, we got 4i for the U component plus 2 minus 3 multiplied by 2, which will give you 8 minus 6. If you want to write it back in INJ, that's also fine. Because the question is given in INJ, you might want to write it in INJ just in case you don't lose a mark. But I don't think they're going to dot you a mark for writing in a different thing. But you should also, just because we're getting a good habit of writing meters per second at the end of our work. Part B, at time t equals 0, the position vector of P relative to a fixed origin O is I plus j meters. Find the position vector of P relative to O at time t equals 3 seconds. Okay. So I recommend a diagram for these. So my diagram, I'm going to do it over here. So draw a nice, reasonably looking diagram. There we are. So we've got our R, we've got our R0, and then we've got our R when we've got 3 seconds. So I up there. I always like drawing this sort of diagram because it kind of makes me think of what's going on. So we know that R0 is going to be I plus j meters. We've got R3, which is going to be coming from S equals ut plus a half at squared, which is 4i multiplied by t equals 3 plus a half times by acceleration, which we know is 2 take away 2 minus 3, multiplied by 3 squared, so multiplying through by 9. That's going to give you 12 of that, which is going to be 21 in the I, minus 13.5 or 27 over 2 j for R3. We just want the position vector of R. So R, if you look at the vector, would be going R0 plus R3, looking at my diagram. So R overall is just 1, 1 plus the vector 21 minus 13.5, which is the vector 22 minus 12.5. And that will do you for question number 1. In the mark scheme, just having a look next to me here, you're not losing any marks for writing it in a different form. If you're writing it in INJ or column, you're not going to lose marks for it. Even in the real thing, you're not going to lose marks. So, yeah, we just need to be slightly careful of some of these. Moving on to question number 2. We got a pulley. Right. Pulley. Before I even start, I'm going to label all the forces on the diagram by reading it. A small stone A of mass 3m is attached to one end of a string. Okay, well, what do I know immediately from that is that I can mark the weight on the diagram being 3mg, marking it downwards. I also know from that I'm going to get a little normal reaction force coming off it. I'm also going to put some tension going that way up the string, and that will be T. I know the tension for B as well, and I know the weight of that because we've got a mass of M, so it'll be a weight of mg. I know all of that straight away. That's an easy mark. We know initially at rest on a fixed rough plane. The plane is inclined to the horizontal at an angle alpha, where tan alpha is 3/4. We'll be using that very shortly. The string passes over a pulley P that is fixed at the top of a plane. The part of the string from A to P is parallel to a line of greater slope of the plane. Stone B hangs freely below P as shown in figure 1. The coefficient of friction between A and the plane is 1/6. That's useful. I'll be needing that in a minute. Write down an equation of motion for A. Okay. Put that back there. So for A then, we're going to look at the sum of the forces, F equals ma, that sort of thing. So we want to resolve this first of all. So we've got, put the pen back on here, 3mg, and the component of the weight would be sine alpha. Thinking about breaking this apart into its components. Doing that, because the sine alpha will be coming down the plane. Minus the frictional force, because we know it's going to be going upwards the plane, and the tension as well is also negative. And that is equal to mass 3m times the acceleration. Using the sum of the forces in the mass times the acceleration, that's all I'm doing there. Right, I know that tan alpha is 3/4, so sine alpha, using a quick diagram, if this is my angle alpha, this will be 3, that'll be 4, so this will be 5, it's 3, 4, 5 right angle triangle, so sine alpha will be 3/5. So you got 3mg times 3/5 minus the frictional force minus the tension is 3ma. So writing it as 9mg over 5 minus friction minus tension is 3ma. And that will do for part A. While I'm here, I'm also going to resolve perpendicular to the plane. So it will know to find the value of r. That will be 3mg cosine of the angle alpha, which we know is just 12mg over 5. Only because I might be using it in a moment, so I also like to think ahead of what the question might be asking me. Because in part B, it's going to say show that the acceleration of A is 1/10 of g for 7 marks, and velocity time graph and all that stuff. Right. So 1200 over 5 is going to be quite useful on a new page here. So friction then, F equals mu r, or the frictional force is mu times r. Mu we saw in the question was 1/6, as it says. And then I've just found what r was, which was 1200 over 5. You can do that all in one go instead of finding the normal reaction first and then putting it in the formula. If you want to do it all in one go, that's also fine. That will cancel down neatly to 2mg over 5. If we look at the motion of B, well, we had just the tension going up and the weight of mg coming downwards. So this is just going to be that the tension is equal to mg for the motion of B. So we can do F equals ma once again, and we can go and say, well, 9mg over 5 minus 2mg over 5 minus mg has got to be the sum of the mass and the accelerations. Alright, so we can divide through by m, which is nice. So you just get 9 over 5 minus 2 over 5 minus 1, all multiplied by g. It's got to be equal to, well, m's cancel out, just give us 4a. That's going to give you 4a is 2g over 5, which means we're going to get a is 1/10 of g. As it wanted. Again, this little equation I formed here was the equation of motion for A. initially, and then I've added b onto it. That's all I've done. Okay. So hopefully this is not too bad. Let's look at the last bit. Sketch the velocity time graph for the motion of B from the instant when A is released from rest to the instant just before B reaches the pulley, explaining your answer. Well, the acceleration of B is constant, so the graph, if you draw it with V and T, is a straight line because the acceleration of B is constant. That's all you want there. In part D, that in relative the string is not light, states how this would affect the working in part B. Well, if the string is not light, that will affect the tension. So the tension on A will be different to B. And that's how you would do part D. Okay, question 2 done. We're moving on to question number 3. See what we got here. Alright, we got a moments question. So, a beam AB has mass m and length 2a. The beam rests in equilibrium with A on rough horizontal ground and with B against a smooth vertical wall. The beam is inclined to the horizontal at an angle theta. As shown in figure 2, the coefficient of friction between the beam and the ground is mu. The beam is modeled as a uniform rod rested in a vertical plane that is perpendicular to the wall. Using the model, show that mu is greater than or equal to 1/2 cot theta. Right. Now, this question is a little bit of a mess if you don't spot what's going on. Because this is a moments question if you've not spotted it yet. And the reason why it's a moments question is because I've got a ladder. And most ladder questions will involve moments, not just resolving forces, unfortunately. So I've got the weight mg, I've got the frictional force on the floor, and I've got the normal reaction coming up from the floor. And then I've got the normal reaction coming up off the wall as well. That'll be n in this case. So it wants me to show that for mu, so it makes sense to take moments. I'm going to take moments about the bottom of the floor, i.e. taking moments about A. So I'm going to do the weight, the mg, multiplied by, it's going to be the length of A, but we want cosine of the angle. You could have also done that by resolving this as mg cos theta times by the length. That's also fine for moments. It's got to be equal to the normal reaction multiplied by the length 2a. And to get that component, I always tend to do these and expand it out that way. So I can just get 2a times by sine of the angle, because I know that that angle and that angle will be just 90 minus it, using a little bit of trigonometry. Hence, I can get that angle out there because I know they must add up to 90. So this will be just theta as well. And then I can use, that will be 2a times sine of it because it's opposite to the angle, which would be the perpendicular distance. That's the way I like to think of it. Resolving vertically then, because that's the three things that we can do in these moments questions. We can take moments, resolve vertically or horizontally. It's the only three things we can do. There's only one bit of weight to consider, so R must be just mg. If we resolve horizontally, we can get that F would just be equal to n. I.e., when I come back down to this, you've got Ra cos theta has got to be equal to 2na sine theta, just subbing in everything I've got. So n then is quite simply Ra cos theta divided by 2a sine theta, which means, therefore, the F then would just be equal to n, which we know is 1/2 R cot theta, But we know that F, the frictional force, is less than or equal to mu times the normal reaction. So a half r cot theta is less than or equal to mu times the normal reaction force. Hence mu is greater than or equal to 1/2 cot theta. That's required. Whew. So, nasty moments question there. It's up to you really how you go about that one. You can do it using the other way of breaking the forces already perpendicular and then times it by the length. That's also fine. It depends on the way you've learnt it, and also if you do physics, maybe you might do it a bit differently to me. That's also fine. In part B, we've got a horizontal force of magnitude kmg, where k is a constant, is now applied to the beam at A. This force acts in a direction that is perpendicular to the wall and towards the wall. Given that tan theta is 5/4 and mu is 1/2, and the beam is now in limiting equilibrium, use the model to find the value of k. So we're looking for the mass. Okay. Right. This is going to get nasty. So the only thing I need to add is the kmg. The problem is, where do you add it on here, on the diagram? Well, where you add it is going to be there. There's your kmg, from what it told us in the question. I'm also going to give these some new letters so don't get them confused. We'll call that Q and we'll call that reaction P. So I'm going to do the same thing. We're going to take moments about the bottom. So, moments about A, the mass, mg is got to be equal to, well, times A cos theta rather, has got to be equal to P times 2A sine theta. Then we want to resolve upwards downwards, which will give me that R is equal to mg. But then the extra little bit is when I resolve that way, horizontally. That will give me that P plus Q is got to be kmg. And that's my little equation I'm going to use. We also know that Q is got to be mu times our reaction force, which would just be 1/2 mg, or mg over 2, also satisfy. So P, we're coming back to this, is kmg minus 1/2 mg. Resolving or rearranging that equation there. Because I'm essentially using this and rearranging it. That's all I'm doing. So from there, that is just the same as kr minus 1/2 of r. So ra cos theta has got to be 2 lots of kr minus 1/2 ra sine theta. Yeah, this is pretty nasty now, isn't it? But I suppose this could be worse. So r is got to be 2 lots of kr minus 1/2 r. This is just a bit of algebra now to get us there, which is sine theta over cos theta, which we know is tan theta, which I will know is 5/4. That'll cancel with the 2, which will give me 5/2 of kr minus 1/2 r. I.e. k has got to be r plus 5/4 r over 5/2 r, which is 9 over 10, 0.9. Yeah, nasty. Quite nasty, this question. Again, that's just algebra work. I'm not going to go through the hell load of that because that's just algebra work. I expect you could do this at this stage. Well, yeah, it's an algebra question. It's not the nicest, I know, but we have to be able to deal with these. Okay, we got a projectiles question. Let's have a look at it. We've got a small stone is projected with speed 65 meters per second from a point O at the top of a vertical cliff Point O is 70 meters vertically above the point N. Point N is on horizontal ground. The stone is projected at an angle alpha above the horizontal, where tan alpha is 5/12. The stone hits the ground at a point A as shown in figure 3. The stone is modelled as a particle moving free under gravity. The acceleration due to gravity is modelled as having magnitude 10 meters per second. Remember, if we are told otherwise to use G, we will use it here. Find the time taken for the stone to travel from O to A. Okay. Well, this tan alpha is 5/12. I'm not going to do much with that because our trigonometry should be pretty good at this stage. What I'm going to do, though, is use our little formula. S is equal to ut plus a half at squared. And just jump straight into this little suiback question. So it's going downwards, so it'd be minus 70. Has got to be 65 sine alpha times by t, just taking the components of the velocity, minus 1/2 times by g, which in this case is 10, multiplied by t squared. Sine alpha is 5/13. I'll just fetch the calculator. Okay, so that's going to give you 5t squared minus 25t take away 70 is set equal to 0. I'm just going to solve that on the calculus, the FX991EX polynomial degree 2. I've got 5 minus 25 and negative 70. That's going to give you values of t being equal to 7, or I've got the value that t is negative 2. Remember, we reject the minus 2 because we know time cannot be negative. So we just need to underline that and reject that. That's all you would have to do to answer that first one. Part B. Find the speed of the stone at the instant just before it hits the ground at A. Right. Just before it hits the ground, I can use v equals u plus at on that. And I know that velocity horizontally has to be the velocity originally, the u horizontally. The reason why I like drawing it like this is if you've got your diagram coming in here, I've got my 60 and my 45, not done much else to that. Because if that's at a slower rate, then doing this diagram should be fairly straightforward because the horizontally for the u would be 65 cosine alpha. That's straightforward. And cos alpha would be 12/13, so that's just going to give me 60. Cool. So the velocity in for v has got to be uv minus gt, which is 65 sine alpha this time, minus 10 times 7. Sine alpha I know is 5/13. That's going to give you, is it minus 45? I think it is minus 45. So I've got the two speeds that I need. So what I'm going to go and do is do that the speed is the root of vh squared, the horizontal component, and the vertical component squared, which is the root 60 squared add minus 45 squared, which I'm getting 75 meters per second. That's what you should get. And part C says state one other limitation of the model that could affect the reliability of your answers. I think it's this bit here, taking G as 10. To make answers more reliable, use G in 9.8 meters per second. As G is approximate in the question. Something along those lines would do there. Accurate value of G. Spin of maybe would also work. There's also loads that you can write for that one. I'm not going to spend forever on it. because it's just 1 mark, and you don't need to feather out for 1 mark. And finally, question 5. At time t seconds, a particle p has velocity v meters per second, where v is 3t to the half I minus 2tj. I'm expecting differentiation and integration immediately. Part A, find the acceleration of p at time t seconds, where t is greater than 0. So, if I've got velocity and I want acceleration, I need to differentiate v. So, in part A, this is like the basics of differentiation. I just need to use the power rule in order to find the value of a, which is the derivative of v, which is just 3/2 t to the minus a half in the I minus 2j meters per second squared. Alright. That's part A done, 2 marks. Part B, find the value of t at the instant when p is moving in the direction I minus j. Well, if you think about your coordinate plane, I minus j is over here, so it's southeast, i.e. we know that I has got to be minus j. Using that fact then, that we got 3t to the half is minus 2t. Not minus 2, minus 2t rather. So 3/2 is t divided by t to the half. Giving you t is 9/4 seconds. Part C, at time t seconds, where t is greater than 0, the position vector of p relative to a fixed origin O is r meters. When t is 1, r is minus j. Find an expression for r in terms of t. So r is displacement. If I've got velocity and I want displacement, I need to integrate this thing. So r is the integral of 3t to the half I minus 2tj, which is going to give you 2t to the 3/2 I minus t squared j plus some constant c. We are told this fact, so we can use it. So minus j has got to be equal to 2i minus j plus some constant c. So c is minus 2i then in that case. So that will be the complete value of r. Just add c on the end. Easy. Part D. Find the exact distance of p from O at the instant when p is moving with speed 10 meters per second. I.e., we know the mod v has got to be equal to 10. So we've got the root of 3t to the half squared plus minus 2t squared has got to be equal to 10. So that'll give us 9t plus 4t squared has got to be 100. That's a nice little quadratic. Let's get my 2 values of t. Why I don't know why not, I do not know. So we've got a quadratic of 4, 9 minus 100, which gives me 4 and minus 25/4. Reject that one, we'll take that one. As t is going to be greater than 0, means t is 4. So I need to sub t is 4 into my r that I got before, my lowercase r rather. So that's going to give you 14i minus 16j, subbing that back in. However, we want the distance, and distance is the modulus of displacement, so I just want the modulus of this thing, i.e. mod r, when t is 4, which is the square root of 14 squared add 16 squared, which is, let's just do that quickly on the calculator, the square root of 14 squared is 16 squared. That one I cannot do in my head. Is 2 root 113 as the exact distance. And let's just double check there's no more questions in this paper. No, there is not. The total mechanics mark is 50. In other words, we've finished it. We finished the paper. Lovely. Right, so that's mechanics then. Should be a lot easier than statistics. I'll give you a forewarning that this mechanics paper is well worth having a go at before you watch my solutions to these. If you've got any questions, leave me a comment. I'll try and get back to you. If you want me to do the pure papers from 2021, I will definitely give those a go if you want me to. And again, you need to let me know if you want me to do that, and I will do that. All right. Thanks very much for watching. See you.